So once again welcome back to Ram Circle class. Today we are going to study a new topic, that is mobility of charge carriers inside any conductor. So this is playing, or this does play a very important role for the conductivity of any material, either it is conductor or semiconductor, and this is not a part of our business in case of what you call insulators. So coming back to the point, let's discuss about the mobility. So this is denoted by a Greek symbol that is known as mu. Okay, so mobility is defined as the drift velocity Vd acquired by any charged particle and per unit applied electric field. Okay, that is the mobility of any charge carrier simply defines how easily the charge carriers are moving through the conductor. So, and it is mathematically is equal to the drift velocity acquired by the charged particle over the electric field applied, or you can say the drift velocity acquired by a charged particle per unit applied electric field across the conductor. So this is a conductor, say this is connected by a battery B of length L. Okay, so electric field will be developed inside it, and that is directed from the positive end to the negative end. And due to this electric field, the charged particles, that is electrons in conductors, we will discuss about different types of conductors. Like first is normal metals, second is electrolytes, in which the transformation of charge carriers or transformation of current is done by whom? The ions, positive and negative ions, no electrons, no protons, no anything else. So for conductors only electrons are the responsible for to carry the electric current. So in conductors the drift velocity of electrons will be towards the positive end. So we know that the drift velocity is equals to, drift velocity of charged particle is given by Vd is equals to the electronic charge multiplied by electric field intensity over m multiplied by tau. Okay, so according to the definition, the mobility mu is equal to drift velocity over applied electric field is equals to small e tau over m and then divided by e. So this e cancels this, that is e tau over m. So mu is equals to E tau over m. Mobility means easiness of for the charged particles to pass through the conductor. Okay, so this is the general relation for the mobility. So in case of conductors, in conductors the electrons are the what? They are the main charge carriers. Okay, so what will be the mobility of electron in a conductor? So we shall simply use subscripts to show the particular notation, that is mu of electron is equals to small e tau over mass of electron. That's it. Okay, this is a general expression, and this is general expression for whom? Drift velocity of electrons taken into account and the electric field applied. So in case of any charged particle, that is for a general case, for any general charged particle, either it is positive ion or negative ion or electron or even a hole. So hole is what? A kind of charge carrier that carries current inside a semiconductor. So we shall discuss about this afterwards in detail, a little more detail. So this E is what? The charge on the electron. So this E will be replaced by a general notation, that is, it's called small q. So mu is equals to q multiplied by tau over m. Okay, this is the general expression for the mobility of charge carriers. Okay, so this is for electron. Now, as I discussed earlier, the electric current is carried in semiconductors by electrons and holes as well. So we shall put a expression for the mobility of holes. So what are holes? First, let's understand this. Holes are simply holes. So holes are simply what? Vacancy of electrons. Holes are simply vacancy of electrons. So let's come into the little bit of discussion. Suppose this is an atom, and this is its positive core. So one electron is lying just outside at the outermost orbit. This is the outermost orbit and this is the nucleus. So in metals, what happens? Okay, the holes are simply what? A kind of charge carriers or current carriers inside a semiconductor, apart from the electron, because electrons are always doing the same, that is to carry current inside a conductor or even semiconductor, but not in electrolytes. So holes are the vacancy of electrons in semiconductor, because in semiconductor all the electrons are bound by the covalent bonds. So at normal temperature, the covalent bonds are, one or two covalent bonds are broken up. So one electron is taken apart from the bond. So what is left at that particular place? That is called vacancy of electron. So that vacancy is simply known as holes. Or in a general aspect, holes is a opposite of electron that carries current in semiconductor. So opposite means it will have a positive charge, it will have same mass, it will have same spin, etc. It will have same parity as well. So that's not a part of our business. We have to simply write the mobility for electrons. Okay. So for holes, the mobility is given by its charge. Obviously, the charge of hole is equal to that of electron. So I am writing E, then its relaxation time over mass of the hole. Okay, maybe you are little more not in comfort, that is in understanding what holes are. So we shall discuss holes in chapter 13, that is semiconductor devices, where holes and electrons play very important role. Okay, leave this now. So now we have to establish a relation between current and the mobility. Very small derivation, let's see. So I is equals to, that is current is equal to N E A multiplied by drift velocity. Okay, and drift velocity is equal to what? Electric field multiplied by the mu. So now put the value of drift velocity Vd here. So then we are getting I is equal to NEA capital E multiplied by mu. That is the relation between current and the drift velocity. Very simple. I, you have to pick, then put the value of drift velocity in terms of mobility, then you are getting what relation between this. So this is so far very simple. Now in conductors like metals, only electrons are the charge carriers. So the easiness of the current or flowing of the electrons is defined by the mobility. The current in a conductor is given by, if it is electron, obviously in case of metals the electrons are the main charge carrier. So for conductors, the current is given by N, E, A, E and mu of electron. Okay, that is the number of electrons per unit volume. We discussed in the last two videos. E is the charge on electron or the charged particle, A is the area of cross section of the conductor, where E is the applied electric field and mu E is what? Mobility of the electrons. Okay, that is current by electronic current or current due to electrons. Okay, now consider a conductor of certain cross section and length as well. So these are holes. Sorry, this is a semiconductor. Like semiconductors examples are germanium, silicon are the two most commonly found natural semiconductors, and there are very artificial semiconductors that's like alloy, that is gallium arsenide, indium phosphide, etc. Today, nowadays we are having organic semiconductors, polymer semiconductors, so many things are there. So in a semiconductor, if current is carried, so holes are the vacancy of electrons, so the bubbles are showing the holes. So what happens to these holes when the voltage is applied? These holes will be drifted towards the negative end. Mind this, these are holes. So this hole will constitute a current, that is I of H, and its direction will be from the positive end to the negative end. In semiconductors, we are especially focusing on this. So in semiconductors, there will be large number of electrons as well. So these tiny dots are showing electrons. Simultaneously, what happens? The electrons are pulled by the positive end. Now see, the current formed by the electrons is in the opposite direction to that of the current formed by the holes. So that is I of electrons, and both type of charges will have different velocity and different mobility depending on their mass and their charges. So if their mass and charges are same, so obviously their mobility and current formed by them will be equal. So now see next, the electrons are moving from the negative to the positive end. So this IE is what? The actual current. In actual current. So generally in circuit problems, what we use is conventional current. So conventional current is always opposite to that of the flow of electrons. Okay, this is conventional current by the electron. I discussed this in the last video as well, so please go for that if you are confused a little more. So this is conventional current that will be from positive to the negative end. Okay, now see that both the currents are moving from the positive to the negative end. So what is the total current? I is equals to I of E plus I of H. That is in case of semiconductors. Mind this. So what was the relation between the mobility of electrons and current? I was equal to N E A, then mu and electric field. Electric field is same for both, but this is the mobility of electrons and that is the number of electrons. So again, for what hole? N E A, mu of holes and electric field. So maybe now in semiconductors what happens, the holes are and electrons are not equal in numbers generally in artificial semiconductors, and pure semiconductors, that is germanium and silicon, are rarely used. So we shall discuss or talk about the artificial, in which both holes and electrons carry the current and they will be different in numbers. Okay, so let the number of electrons in any semiconductor is not n, rather it is n1. Number of holes in that particular semiconductor is n2. So small e, a and e is taken out, so we have n1 mu e plus n2 mu of h. That is the expression for the total current in a semiconductor. Okay, this is a expression for the current in semiconductor, and for conductor only what we had, I is equals to n e a mu and e. So this is the relation for drift mobility and current in conductors only. Okay, only little more different from this. What is this? You can perceive this from. Okay, this is the relation between the mobility and current.